Hi, Nancy.
Hey.
So I wanted to ask you, I don't have a quiz for you today.
Of course.
I don't have a quiz for you.
Oh, you don't?
No, I'm saying. No, I have a question. Have you ever been, how to put this, like, I want to say like the keeper of the key or like responsible for like
Yes.
doling out something?
Yes.
What
yes.
was it?
This is kind of random. It wasn't like a thing, but this is kind of weird. And I can't even believe that they entrusted me to this.
I'm so excited for this.
Well, as you know, I was a chemist.
I do know. There's an earlier episode where I did not know this, and I will never live this down. Thank you.
And I worked at a pharmaceutical company. And at some point in my time working there, I became the radiation safety officer. And I was responsible for our very, very, very small little lab that had radioactivity in it.
Define responsibility.
I was the radiation safety officer, so I was responsible for that lab. I was responsible for all the, what was coming in, what was going out, how people were trained, and making sure it didn't like get all over the place. I mean, it was very low level radiation stuff, but still, I had that responsibility on some level.
You have to like run through with like the Geiger counter.
Yeah, totally. And like make sure. I mean, there were only a couple of us working in there, so it wasn't a big deal. I was like, my name was on like, something document.
Man, that's impressive. All I can think about now is I'm currently watching Chernobyl.
I do, but I haven't tuned in yet. But it looks good.
Oh my gosh, I've never been afraid of like radiation because it's just not something I encounter in my daily life. But just like I'm terrified now of just like what it could do to me. You had that responsibility, Nancy.
Yeah, I know.
That was a big deal.
Yeah, it's pretty crazy.
Welcome to the American Geophysical Union's podcast about the scientists and the methods behind the science. These are the stories you won't read in the manuscript or hear in a lecture. I'm Shane Hanlon.
And I'm Nancy Bompey.
And this is Third Pod from the Sun, Centennial Edition. All right, so we're talking about this today. We're not talking about, well, indirectly, I guess, but not really talking about radiation. We're talking about responsibility.
True.
And
being responsible for something that's like, way more thing than I was responsible for.
Really important.
Yeah. So I talked to the guy who is responsible for the moon rocks, the samples that astronauts brought back from the moon.
So I'm Ryan Zeigler. I'm the Apollo sample curator at Johnson Space Center, and I take care of the moon rocks.
Awesome.
Yeah.
So what does that mean? What do you do?
So I'm the curator for the Apollo samples, so it's my job to keep them safe, but also to make sure scientists get to do science on them so that we can learn as much from them as possible.
So how did the astronauts get these when they were on the moon?
It evolved over the 6 missions. So at the beginning, it was pretty simple. They had a scoop and a box, and Neil walked around and just scooped everything up and dropped it in the box, and that was kind of all there was to it. In the later missions, they got a little more sophisticated. They designed a rake that allowed them to rake through the soil, leave the small stuff behind, and get the sort of walnut-sized samples and bring those back. They had a drill core. They had drive tubes that they would just hammer into the surface. They had rock hammers that allowed them to break off pieces of boulders. So it kind of evolved from a simple pick it up on Apollo 11 to the same tools a field geologist would have on Earth by the Apollo 17.
So from Apollo 11 to Apollo 16, what were their choices, I guess, what they were sampling?
Yeah, so the 6 missions went to 6 very different locations, and the first 2 went to flat basaltic areas because they were safe, they were near the equator, so they had the most delta V available, they had the most fuel to get down and get off, and it was flat, and they weren't worried about landing in a crater, which Apollo 11 almost did anyway. I don't know if you've seen First Man.
I did,
but the part where he had to go on manual and fly over the big crater, yeah, that's totally real. Anyway, so they went to safe places first, and we learned a lot about the interior of the moon from the Apollos, from these basalts, because they're what tells you about the interior.
And what's a basalt? Does that mean?
So a basalt is probably the most common rock type at the surface of the Earth. It's what's coming out of the volcanoes in Hawaii. And so what you see erupting out in Hawaii, that's a basalt. It makes up the ocean floor. It's found on almost every terrestrial planet we've ever looked at. And so it's a basic rock, but it's a really important rock. It's common, but it still tells you something really important and sort of fundamental about the planet. Plus, it was safe, and astronaut safety was paramount, and so that was great. Once they had done that, then they went to Apollo 14, which was in the Highlands, kind of a weird part of the Highlands that was from this big impact crater called Imbrium, the Imbrium Basin on the near side of the moon. And then by Apollos 15, 16, and 17, they were confident, and so they went to much more geologically complex and much harder to land. I mean, the stories you hear Dave Scott tell about coming in on Apollo 15 over this thousands of meter tall mountain and then having to land quickly to get down to the surface. They're sort of harrowing. And Apollo 17 landed in a valley, Taurus-Latrobe Valley, that's really narrow. And so they came in and landed on the basalt in the middle with all this anorthosite, the highlands on both sides. And so by 15 and 17, they were landing in these geologically complex areas, which is why the samples from Apollo 15 and 17 are the most requested, because they're at the junction of these two major terrains on the moon, and you can learn about both of them from one set of samples.
I feel like we're going to need to define we're talking rocks. We need to define some terms. We talked about basalt, what basalt is.
Right. And that's very common here we have that here on Earth too.
Sure. Yeah. I mean, frankly, I say sure. I have no idea. I have a PhD in biology. I know nothing about geology. I never had to take a class. I'm a bad scientist when it comes to that. I should know better being at an Earth and Space Society. Anyways. Okay. Another one, anorthosite.
Right. And that's another type of rock that we don't really have. We have it here on Earth, but not really the same kind.
Okay.
And what Ryan explained to us was that the basalt is like when you look at the moon, it's like kind of the dark areas. And then the anorthosite, if I'm saying it right, is kind of the brighter areas.
So it's like dark meat, light meat.
Yeah, sort of. Sure. So those are the two different kinds of samples.
And there's another one. Breccia?
Yeah, which is actually what Ryan studied, and that's just like rocks made up of other rocks. So each little piece of that rock made up of all these other rocks, and you can study all these other rocks, and so it's very interesting to study as a scientist, I guess.
Neat.
Since the dawn of time, mankind has stared up at the heavens and wondered what was contained in their vast...
So how many did they bring back? I mean, how many samples are there?
So there were 382 kilograms, 842 pounds of rocks originally, and about 2,196 individually numbered samples.
Wow. Okay.
Yeah.
Okay.
Approximately.
And how big do they range from? Like, are they all about the same size?
They range from basically micron-scale motes of dust to, I think the largest sample is almost 13 kilograms, so a little over 25 pounds.
Oh, that's pretty big.
Yeah.
Okay.
Yeah. So everything from, a rock you would not be comfortable holding. I think the average size is probably the size of an egg, maybe a little bit bigger. Yeah, there's 2,200 samples there. Yeah.
And I guess I've seen pictures. I mean, we all probably have, but what does it look like? Or when like for you who work with these, like what can you describe what they look like, what they feel like, what they,
Sure, they're kind of boring to look at, which is sad to say, but no, a lot of them are breccias, and so they are gray rocks made up of pieces of other rock, and they're really important, but on Earth, we have all these beautiful minerals that are blue and red and green, and we don't have that on the moon. We got one green mineral, we got some nice white minerals, but by and large, they tend to be mostly gray. There's a few white ones. There's a few sort of one that has peridot in it, so that's our pretty rock. We use that for display a lot. And then the soil is, of course, just a pile of gray dust. You wouldn't think anything of it if you didn't know where it came from. You might just think it's something that got swept up off the floor, which is not where it came from, just to be clear.
Where do you keep them? How big is this room? How many are there?
So for the Apollo samples, we have a special building at Johnson Space Center called Building 31 North. We're not great at naming things. And it's the Lunar Receiving Lab. It used to be called the Lunar Receiving Lab. Now we don't have a cool name for it. But we keep them in a clean room and inside a vault. And that keeps them safe but clean.
And how big is it?
So the building you wouldn't recognize it from the outside. I don't want to undersell it, but it's this square building with no windows because it has to be hurricane proof. So it's very function over form in this case. But I don't know, it's maybe 1,500 square feet, I think, total for all the labs that we keep the Apollo samples in.
And how are they stored? Like, how do you store them to make sure they're good?
We keep them inside nitrogen cabinets. So we have these big stainless steel nitrogen cabinets with little stainless steel bins in it, and they're sealed inside Teflon bags inside that. So that keeps the oxygen and the water in Earth's atmosphere away from them and keeps them from rusting, essentially. You only get to have one bad day at work, where I work. Like, you have a bad day and you left a valve open or something and air gets in and it's like, I can't take the air off the samples now. If somebody pours water on the sample, the water's seen on. No, it's what keeps me up at night. And I mean, there was the facility in Canada, the ice core facility, that had a freezer go bad overnight, and they came into puddles on the floor. And everyone I know sent that to me. I'm like, stop it. Stop it. We have frozen samples, not ice samples, but we have samples we've kept frozen for 40 years. And if we come in one day and our freezer's no good, and we monitor it so that won't happen.
Right.
But it's terrifying, just terrifying.
Right. If something gets on it, that's it. There's no, I
mean, people ask me what...
That would keep me up at night, to be honest. Yeah.
People ask me, like, whether my job is fun, and I'm like, it's equal parts fun and terror, because terror is probably a strong word, but nervousness, because it's just that. It's, oh my God, this is so cool, and oh my God, don't screw this up. And it's sort of those two competing things.
That does sound actually pretty terrifying. I mean, I get like worked up about, sending like a wrong email.
I know, yeah. Like if I take my job very seriously, but like if I have a bad day, it's like, yeah, I reply all to the
staff email.
Right, exactly. Like send us all your email things. And like, here's my very specific thing, which I gave a colleague a hard time for that the other day. I was like, good morning to you too. And she's like, don't even talk to me right now.
What have they learned from those later samples about the moon?
Oh, man, they learned so much. So on Apollo 11, the best story from Apollo 11 was Neil deciding that the rock box looked not full enough. So, he went around. I didn't realize they only had 2.5 hours in the EVA on Apollo 11. And on later missions, they did 7.5 hours in a single EVA and multiple EVAs. So they only had 2.5 hours. So they split up the work, and Buzz went over and did all the geophysical work, and Neil went around with a scoop and picked up rocks and took a lot of pictures, which is why he's not in any of them. Anyway, he gets done, and there's a rock box sitting there. And before he seals it up, he's like, that's kind of empty. This seems like a waste. So he gets a shovel and just literally shovels 4 or 5 scoopfuls of dirt in there. And it ended up being 20% of the mass brought back from Apollo 11. And a guy named John Wood at the Smithsonian studied the small particles in that, and he found a rock type called an orthosite, or what he thought was an orthosite. Tiny fragments of plagioclase feldspar. So he decided that the moon formed through a giant impact, and that there was a magma ocean covering the entire moon, and that crystallized, and that the plagioclase floated, and the other thing sank. He came up with this crazy idea of how the moon formed, which totally turned out to be right. But
based on
1 millimeter particles in one soil from one thing. But they couldn't prove it because the samples were too small to get an age date on, so they had to be ancient. So on Apollo 15, one of the reasons they went there was on the rim of this giant basin, and if any of this ancient crust was going to be on the moon, this was the place to find it. So the joke I like to make, maybe not on a podcast, is that you could train an astronaut to look for a white rock. And they did. They were like, look for the bright white anorthosite rocks. And sure enough, like a couple hours into the mission, they're like, we think we found it. They chipped it off, and it became the Genesis rock, 15415, and they brought that back, and they got an age date on it. It was 4.42 billion years old, almost as old as the Earth itself. And so that sort of confirmed that there was a magma ocean on the moon. And then later work sort of nailed down the giant impact origin of the moon, and yeah. They started to pick the later missions to prove theories that had been proposed from the earlier missions. It wasn't just that. I mean, hearing Jack Schmitt talk about this, so he was the only astronaut who went to the moon who was a geologist by training. Okay. And so he had a lot of say, if you believe him, and I do, that, where they were going to go. And there was a lot of debate. Some people wanted to go to Tycho, and some people wanted to go to Aristarchus. And, deciding where to go was hard, especially once they knew that Apollos 18, 19, and 20 were canceled. And they only had 1 or 2 shots left, so it became much more of a debate.
So your advisor had actually worked on those Apollo missions?
In 1969, he was one of the 40 or 50 pre-approved scientists. He was at the University of Wisconsin, and he got samples within weeks. I mean, whenever the quarantine ended, which was about 3 weeks, all of a sudden samples were being processed and sent out. And he did neutron activation analysis, so he irradiated them and then put them in front of a detector to see what elements were inside of them. So some of the very earliest bulk compositional measurements of the moon were done by him. The stories about the early Apollo scientists were colorful, and the science that was going on and how fast everything was moving. It was a much more relaxed pace when I came in the 90s. My first question to Larry when I sat in his office as a prospective grad student was, you study the moon? It's been like 25 years. You guys are still working on those? And he just looked at me. I'm like, can I take that question back? And he's like, no, it turns out you can't. And he had given me a Mountain Dew, which I hadn't opened yet, and he reached over and he started to slid the Mountain Dew away from me. Joking, I think. And anyway, and so no, I mean, yeah.
It is pretty crazy, to think about that the stuff that they collected, 50 years ago, they're still using today to, do new science on.
Oh, yeah.
I mean, think about, I know, you go out in the field, what if you had, I don't know, do you do that, 50-year-old lizard or something?
Yeah. For those of you who are not aware, I'm a herpetologist by training, and yeah, maybe no, not even a turtle. No, yeah, it's different, but no, I can't imagine things still being relevant. Yeah. I read a scientific manuscript from 10 years ago. Right. I'm like, this isn't right anymore.
They're sealed, like you said, and they're in bags and things like that. How do you get them then? Like if a scientist wants to use it to do whatever for it, how do they get it?
So they're usually stored if they're a big rock, they're stored just in 3 Teflon bags. If they're a smaller rock or soil, they're inside of like a stainless steel or aluminum canister and then bagged inside that. So short version is we cut the outer bag off. So we'll take it out of one cabinet, walk it through the labs in air. Before we put it into the airlock for the next cabinet, we cut the outer dirty bag off. It's not really dirty, but it's dirtier. And then with clean gloves, we put it into the airlock and we flush it to drive away the oxygen in the water. And then we bring it inside with a clean bag. And then once inside the processing glove box, we can just open it. And then they work on it with stainless steel tools or aluminum tools or Teflon tools. And that's it.
They have to do that there. They have to come to you to use it.
They have to come to us to get them, but they can work on the samples in their own laboratory. So most of the scientific measurements don't actually happen in our lab. So occasionally a scientist will come in because they have something non-destructive they can do, like remnant magnetization. So they can do that in the lab through the bags, and that's great. We don't have to send samples out. They don't have to come back. Usually it's us chipping off a few grams of sample or even less and then sending it to them, and then they work on it under the conditions in their lab that they know don't contaminate their analyses. So we try to keep it clean for all analyses all the time. Once they've been approved to do some work on it, we're less worried about contamination that doesn't affect their study. So if they have to dissolve it in acid anyway, as long as they handle it in a way that doesn't bias their measurements, we're good.
You're good. It doesn't come back. I mean, that's...
Oh, it does come back.
It does come back.
Oh, yeah. Everything
okay.
is alone. No. No one gets to keep moon rocks. And so if you had permission, that's let me say that again. No one gets to keep moon rocks. No, the scientist has to propose what they want to do to the sample, and that has to be approved. So sometimes they get approved to dissolve it in acid and study the isotopes, or to irradiate it, or do other things, and that destroys them, and so those don't come back. But as long as there's sample left over, it has to come back to us. They fill out a sample report that says what they did to it, and then when someone else wants to do later work, if we can reuse the sample, we will. It's not always easy to get them get new scientists to use old samples because they don't trust the other scientists. It's usually just everyone's busy. So did you fill out the form right? But we've had really good successes. One of the reasons we have so much of the Apollo samples left is we've been able to reuse them whenever possible.
Oh, okay. I didn't realize that.
Yeah.
So you try to reuse them.
Yeah, whenever possible.
Yeah. What do the scientists do on these? I mean, and to someone who's not very familiar with science, familiar with science, but maybe not a geologist, what are they doing on them? What are they looking for? What have they found in the times that you've been doing this?
I mean, I get about 60 new requests a year to study the samples for about 700 of the subsamples of it. It's everything from the normal stuff you would expect, like mineralogy, geochemistry, to study the moon. How did the moon form? How did the moon evolve? Stuff like that. So that's our pretty standard stuff, but they also get used for toxicology. So the astronauts reacted to the dust while they were in that environment, and they weren't in it very long. So people are actually using little bits of the dust to find out how toxic is it. The answer isn't very toxic, it's just sharp. And so there isn't something chemically about it, I think, that is bad for humans. They've even used it to try to study the galaxy as a whole. And so people want to know whether the flux of galactic cosmic rays has been constant over time. And so you need samples that have been sitting in the galactic cosmic rays for billions of years as the Earth and the whole solar system spins around the center of the galaxy. Does our relative position in the galaxy change how much radiation we're getting from the galaxy itself? So people have studied that. So it's everything from geology to cosmochemistry to cosmology to health. And everything in between.
All this stuff they can learn from the moon rocks. And
all from the moon
and
rocks.
some of the stuff that they can learn from the moon, they can't learn from the stuff that they do on Earth. I mean, is that just because it's been kind of preserved, or why is it better to look at the moon stuff, I guess?
Because the moon rocks are older. I mean, almost every rock from the moon is older than every rock on Earth. So almost all the rocks on the moon are more than 3.5 billion years old. And there's like 5 places on Earth where you can find rocks that are 3.5 billion years old, and none more than 4 or 4.1 billion years old. So that first 500 or 600 million years of solar system history and the Earth's history is just lost on Earth. So by going to the moon, we can study that. And it's not, there's a leap to go from what you're learning on the moon to what you're learning on Earth. But scientists are smart, and they're pretty good at making leaps.
And could you describe what you're looking at over?
And what are some of the things that people are using the samples for now? I mean, what are some of the newer things that people are investigating with the Apollo samples?
So for the longest time, we thought the water was dry. Just bone dry, which is a terrible analogy because bone is 30% water. But people have always no, seriously, the number of times I heard the moon is bone dry, and I'm like, stop using that phrase. Anyway, so if you would have asked any lunar scientist in 2000 2008 or to even 2010, does water have any moon in it? The answer is no. We've looked at all the rocks, and none of them have minerals that have water tied up in them. Obviously, there's no water deposits. Not like Mars, where you see evidence for liquid water at the surface. There's no atmosphere. So the moon was a dry place. And then in 2008 to 2010, 2 different sets of researchers looked at 2 different types of samples, and they found some water. One in the pyroclastic glasses, and then in a mineral called apatite. And that one was particularly important because apatite is in most lunar rocks, including the basalts. And it just turned out that instruments and maybe the thinking behind the moon had changed enough that now we were seeing hundreds to even thousands of parts per million water in this one mineral. So it's still a pretty dry place, but there was some water, some volatile component that in the original moon, this wasn't added later. And so that changed a lot of, so people have been trying to tie down what volatile elements they're there, how depleted are they, and they're going to ever more or ever less volatile elements like zinc and tin, things we don't think of as volatile, but metals that vaporize at a relatively low temperature, to try to understand the dynamics of the giant impact origin. So if you're going to have a giant impact and smash some impactor into the Earth and everything's going to melt, how do you preserve any water at all in that? How do you preserve any volatiles at all in that? And so now they've had to change their models on how that works. And I don't understand the models well enough as a geologist to sort of critically evaluate them, but the smart people who do it say that this is really important. If we had more samples from other ancient bodies like Mercury or asteroid sample return, or maybe even Mars, we might be able to use those to answer these questions. But right now we have the moon, and the moon is not a very active place. It didn't have plate tectonics. It doesn't have wind and water erosion. So this is probably the best place to study the early solar system, which is one of the reasons we need to go get more samples. The Apollo samples are still viable. We learn a lot from them. We're going to learn stuff from them for decades. But they raise questions that can't necessarily be answered from those. The area that they sampled on the moon is about the size of Texas, maybe a little bit bigger. And so if you tried to learn about an entire planet from the rocks from one location, I'm not trying to sound greedy, but that won't work. And so if you could get samples from the far side of the moon, if you could get samples from the near side highlands in a different place, if you could get it from Aristarchus, you could answer fundamental questions about the moon and about the solar system, particularly about how impacts have affected the solar system throughout its history. And so we really need to get more samples. Opening new samples is the most exciting thing a curator ever gets to do. Like, I hope at some point in my career, new samples come back from the moon, and I get to be there when they're being opened, because you don't know what you're going to get. I mean, it's the close to field geology that a planetary scientist gets to do. I mean, we don't get to go out and just grab new samples whenever we want. So it's going to be super exciting.
Roger, Eagle, I'm done. Roger, you'll give us crew and data. We got the modes for you.
Being pretty familiar with the samples, are there ones that, like, I don't know, you have an affinity for?
There are, and I didn't realize it until I became the curator. Like, I did my PhD on Apollo 16 mostly, and then Apollo 12, and so those were the ones I knew the most about, and so I was always using those, and I realized that's not everyone's favorite. I mean, everyone has a different favorite. People come in the lab, and they're super excited about the Apollo 11 samples because they were first, and Neil collected them. That seems to be a big point. And, and I had never really thought of them as anything other than high titanium basalts. I missed the cultural significance of them. So, yeah, Apollo 16 samples are sort of near and dear to my heart. They're also they're complicated. They're from the highlands. They're all breccias. They're a pain to work on. It's way easier to pick up a basalt and study that than to pick apart a breccia and try to find what all the different components in it are. It's really important because it tells you about the bigger history of the moon, but it's a pain.
Altitude, velocity, light. 8.5 down, 220 feet.
So what is it like? I mean, for you, I guess you do this day in and day out, and I'm sure you've been asked this question before, but what is it like to hold a rock, first of all, in your hands that came from the moon, and then second of all, like the origin rock, like that, like this is the oldest thing that anyone's probably ever held? I don't know.
Well, so full disclosure, I don't get to hold the rocks very often. No, so, I mean, it's funny. As the curator, I, review the science that's proposed, and I go up in the lab and I help. But I have processors who have been trained on how to actually physically break the rocks. And so Andrea and Linda and Sharice and Jeremy and Carol, they do all the real work. That said, I still put my hands in the cabinet when they're not looking, just as you said, to hold the rocks. It hasn't stopped being fun after 7.5 years, and that's after 12 years as a researcher in my own lab holding samples there. And so it really, you just stop and think about where they came from and what went into getting them. $125 billion in current money, 500,000 people maybe working on the project, just all the sacrifices that were made by all those people to bring the samples back. And yeah, it's sort of humbling. It's easy to take the extra effort to take good care of them.
6.5 down, 5.5 down, 9 forward.
There's a reason people have worked there for 46 years, 45 years, and 44 years, because they see them not as theirs, but they see them as they're invested in the samples and taking care of them for the world.
Okay, engine stop. Houston, Tranquility Base here. The Eagle has landed. Roger, twang.
I know it's becoming kind of a worn trope at this point with my views on space. Not appreciating space as much as but I mean, honestly, it is starting to change. And stuff like this is just so fascinating. Like, it gives you such at least me, it gives me a greater appreciation kind of for like what folks went through. Like,
totally.
What this was at the time. And it's so cool. Like you said, we're still learning stuff from this now, like now 40 some years later.
Yeah, so the 50th anniversary is coming up July 20th. So of the first, Apollo 11 landing on the moon. So that's really cool. And and it's really interesting because a lot of what they're learning also is being translated into like we're going to asteroids and bringing back samples, and hopefully to Mars and bringing back samples. And so a lot of what they've learned about how they treat samples and how they give them to scientists and what they're learning from them. And, it started with this stuff, with the moon rocks. That was the first thing that we had,
Super neat.
Very cool.
Yeah. All right, folks. Well, that's all from Third Pod from the Sun Centennial Edition. Thanks to Nancy. Thank you, Nancy, for bringing us this story.
You are welcome. And thanks, of course, to Ryan for sharing his work with us.
The podcast was produced by Nancy and mixed by Colin Warren.
We'd love to hear your thoughts. Please rate and review us on Apple Podcasts. You can listen to us wherever you get your podcasts, and of course, always at thirdpodfromthesun.com.
And be on the lookout for more Centennial episodes to come,
as well as our regular episodes.
All right, thanks all, and we'll see you next time.